Okay, so let's get started. Let's see. So this will be the last lecture. So this will be the last lecture from me. So we will basically finish our discussion by deriving LSD reduction formula. The question of how to extract S matrix from a Green's function, so which we will see today. And then on Wednesday, there will be a lecture. And Young-ho will teach you lecture on, I believe, the representation of a Poincare and how to think about the spinors and vectors and so on. So this will be good sort of a thing to understand. And then based upon next semester, I believe Professor Yan will develop further, including QED, loops, renormalization, RG, and so on. Okay? So this is not the last lecture. There will be a lecture, and Yomo is absolutely awesome group theorist. Okay? No, we are actually writing a group theory paper right now. So he knows more than probably anybody around me about the group theory. So I strongly recommend you to come and learn about the group theory, or rather, representation of Poincare and spinors and vectors. Okay, any question before we move on? So then next Monday, so 1 week from now, is that right? There will be a final exam. Is this the first time you hear about that? Are you shocked? This is the first time you hear about this? Hold on, really?
About Monday, yes.
You knew it, or you?
I didn't know about Monday.
You didn't know about this. Okay. But that information is on somewhere on the, I guess, university website, right? Right? Who's taking this for credit? Let's make sure. Is this your first time hearing about this exam?
I think I've seen this, that the it will be held in.
Who's shocked? You're shocked. Okay. Somebody got shocked. Okay. It's better than you hear about this Friday. Okay. So there will be a final exam next Monday. I think TA will send out where and what time. Okay, but sometime next Monday. Any other questions before we move on? Okay, so let's go. Are you okay? You're okay? So today we will basically discuss LSD reduction formula. So this is, there is a good chance that I might miss some spells. Can I expect help? Probably not.
Anyway.
Huh?
That's right.
Man.
That's fine.
Music. Twam. Hopefully. This paper is long time ago. I think the title of the paper was in English translation. Okay. So this is certainly the time when people had to think through really the fundamentals of quantum field theory. Okay, so if you recall, the question was given a Green's function, okay, k1 to kn, okay, how to extract S matrix? That was the question. And last time, we sort of discussed a setup where we can now do something. And that setup was that the first thing we discussed was if you have an operator, suppose I have a Hermitian operator, for simplicity, then, and then if I have a fx, which is such that this is positive frequency solution to Glenn-Gordon equation, so e to the I k dot x, so this is the positive frequency solution to the Glenn-Gordon equation, then what we discussed was that first of all, we can sort of project this guy onto a one particle sector by doing this, right? And if you do this, basically you get limit equals to minus infinity equals to plus infinity, and then what we call this operator, where that operator looks like a f. And then what we talked about was that if we apply this to, say, operator phi that we used to talk about so far, right? So remember this Green's function in position space is time order of Heisenberg picture operator, and then this operator did not be either elementary field nor free field. It can be arbitrary field of the field theory that you're dealing with. Then what we have shown was, for instance, if we apply this back to that operator, whatever I'm interested in, meaning the operator whose correlation function we are interested in, then we found out that in the limit, either plus minus, and some fixed state that need not be specified. And then if we apply that operator, so this, and then for technical reason, we say that we are going to use a renormalized operator. And then the renormalized operator is related to the Heisenberg picture operator by this relation. Okay, although we don't really have to do this, but it turns out to be useful. So if I do this, acting on this vacuum, it acts as if it's creating a one particle state with, in particular, not just a random one particle state, but wave packet state with F. Okay, this F is a wave packet profile. So this becomes F. Okay, so that's what we talked about. And in fact, if, for instance, this one, if we ask a question of a multi-particle state, we found out that the overlap is 0 because the exponential factor never dies out. Okay, so that's what we talked about. And then, so therefore it acts like it is a creation operator, if you like. This is in B1 with some profile F. Right? That's how it acts. But then we also talked about the fact that, on the other hand, this only acts like a creation operator, for instance. So it does not act like annihilation operator. It only acts like a creation operator. Then we can define an analogous object like this. Suppose now I construct the similar projection. Now with F dagger instead. Okay. If you do that, in this case, you get similar result like this. The first thing is now the order flipped. Okay, so now you get plus infinity first, and then minus infinity. And then the operator you get out of this projection this time is a dagger of what you have thought. And then the dagger operator first of all minus because this is Hermitian conjugate. And then A star here I'm assuming the Hermitian operator. That's why you don't see any A dagger explicitly appearing here. But basically, this got only complex conjugated, including this vector. Now, this operator, on the other hand, just like this is as if it is a creation operator only. If you construct this operator for phi over R operator, you get the annihilation operator, basically, associated with that. So now you can guess what this will do if you apply that to this operator that we're talking about. So in this case, as t goes to plus minus infinity, so if I do dagger with some fixed state, and then if this is a one particle state, then what it does is that it will project on this. So now this will perform, or this acts as if it is a annihilation operator of a particle state with a wave vector profile F. Okay? And then just like what you have seen here, on the other hand, the same limit. Instead, if you use it the other way around, you get 0. So this now has only an annihilation operator effect. Okay, so that's what we sort of talked about. Although I didn't prove this fact yet, which I will do given if we have time. But I mean, I want to first use this fact to talk about the LSD reduction formula. Okay, and then at the end of the lecture, if I still have time, I'll just prove it, because proof is straightforward. It's not even, it's just integration by parts. All right. So, moving on to here, before we actually do this, let's discuss two particle, let me just write in or out states, meaning asymptotic states. Okay? So now that we know how to project some general operator onto one particle sector, the question is, can we construct in and or out state using them? Okay, so that's the question. And you already know that you can create a one particle state out of this, right? So if somebody hand you this general operator phi over R, which can create not only one particle state, but many particle state also, but you know how to use that to construct just the one particle state, right? So one particle state is good. So suppose you prepare a F1 state, if you like, by, you can take either plus minus, F1T acting on the vacuum. Now, is this in state or out state? Well, you don't know yet. So for one particle state, basically in or out state are the same. Why is that? Remember, what was the definition of in or out state? The state is that there is a quantum mechanical quantum mechanical state which comes from the interacting quantum field theory. But if you take a time limit to either minus infinity, that looks like free particle state. So you have a very completely general interacting state. But if you look at a minus infinity time, that looks like a free particle. You called it a what? In state. But if you, on the other hand, look at the plus infinity part, it looks like a free particle, we call it out state. So it's just a labeling scheme, right? Now, for one particle state, there's a one particle isolated and non-interacting state. What would it do? It looks like a free particle in the minus infinity, it looks like a free particle in the plus infinity. So it doesn't matter whether you call it an in or out state. It doesn't do anything funny, it's just a go pass through it, right? So at this point, I don't have to label whether it is in or out yet, okay? So I'm just taking it. Now, let's take a second operator. So now, introduce the second one. And then, now, second profile. Okay. Now, you know what this guy does if you're acting on the vacuum either at plus or minus infinity. But now we want to ask the following question. The question is, if I take this guy and then acting on this state, right? What is it? So that's the question. Okay? So what is it? And just like what Hong did, I will just give you physics argument. And then full mathematical rigor can be found in one of the paper he cited. So the physics argument goes as follows. Suppose you had prepared a one particle state that has a wave packet profile of F1s, okay? So you had some states. And to be concrete, let me just take, to be concrete, let's just take the first example. So let me just take a plus infinity example. But the other case it is equally fine. Let's just take a concretely this example. So you had a one particle state flying, doing the free flying, and then you wait a long time, right? Because you're going to use this guy only at plus infinity time. But say we wait super long time, and then there was a one particle, F1, passing by, and then I waited a long time, and then we are about to use this operator, projected operator, onto that state, where one particle state is right there. It's not a vacuum. What I'm going to act on here and see what happens, right? That's what this thing does, this expression does. So there was a wave packet state. So suppose this is my time t. And then there was one wave packet state, F1. Okay, and then you waited a long time, you will just do the pre-propagation. You go to some momentum direction. So let's label it a momentum direction, like so. And then it goes that way. At some point, you act on a point in space and time x, which what we want to know basically is that these 2 points, whatever, like the center of this wave packet, when I'm about to act this operator at space and time point, if that is space-like separated, say, what I do here should not be affected by the presence of another wave packet state, because that might be space-like separated. So in fact, in order for this argument to go through, we will not need infinity to be involved, right? So long as there is a one particle state and it's somewhere there, but so long as when I'm acting the second one to produce this guy, so long as the separation is a space-like separated, therefore causally disconnected, right? It acts as if I'm acting this operator on the back, okay? So that's the physics argument. Hence, so that now here we are creating another wave packet, probably going to different momentum direction. Okay. So after all, it will look like I will have a 2 wave packet state moving potentially with a different momentum direction. Is that clear? So the only coincidental point that we are not sort of assuming not to be the case is that there is a one wave packet state when I'm about to act like this guy is literally sitting right there, right? And then obviously it's unclear what we are doing. But other than that, it should be clear that basically we are preparing a 2 state with 2 wave packet. But then the question is this in state or out state? How would this look like? You might say, oh, that looks like there's a one particle state with the wave packet 1, and then another state with the wave packet 2. But at what time it looks like that? Well, it looks like this at time plus infinity by construction. So then this will be what? This will be out state. Is that clear? You could have asked the other case, what if I have done this? Then what would it be? The same argument. There was a state, but then so long as there is this long separation, no causally connected to each other, I'm creating a second guy. It shouldn't be perturbed. But then it looks like 2 particle states with 2 different wave packets. But at what time? Well, in minus infinity time. In that case, this will be proper to be called as an instant. Is that clear? Yes.
Why don't you consider the timing that's going to be create the first one particle state? F1.
Why did we consider this?
Consider the time index.
In principle, I guess in principle we can write, first I'm writing this and then on top of that I can add the second one. In fact, that's what we will see in the process of proving L is Z fully. Here I just assume, one particle was already prepared, but we could have done that in sequence, right? But here what I'm requiring is that so long as there is a clean separation at the time and then different momentum direction, okay? There should be a notion that I first prepare a particle going that direction, and then I'm about to prepare a second particle, which is far enough, in a sense of causally disconnected and so on, that the presence of the first bomb shouldn't affect what I'm doing on this part of the space and time. So I can create the two particles. That's basically, so you can label the time. But what really matters is, it's not quite just sequence in the time, but probably I could have done this simultaneously, right? So long as they are space-like separate. That's what I would say. Okay. Good. So probably I already said what I said. Remember, given this wave packet state, there is associated profile, if you remember. Okay? And then there is another thing, and then there will be also profile. More precisely, this was basically given a wave packet state, if I projected onto the wave momentum space. There was a definition. Okay? Now, in order for all this argument to go through, basically what we are assuming, also partly addressing the previous question, is that these two are sort of non-overlapping. So there is no, so basically what I want to say is that okay. So here so this equation encode what I mean by non-overlapping two wavelengths. So let's check whether that makes sense. So you can draw naively in momentum thing. So I'm talking about basically one packet localized with respect to one central value, second one localized with respect to the second. So that's naive drawing of that. But what is the real physics of that? What does this tell you is that you have a wave packet with the center moving at certain direction specified by the momentum of the central point, right? This is the second bomb moving also a certain direction, governed by the momentum direction of this thing. So here, what we are trying to say basically physically means that I have two wave packets. They move along the separate direction. But that means that, do I have any part of this wave packet moving exactly the same direction, meaning same momentum with a non-zero overlap? I'm basically considering, I don't want to talk about that kind of case. So in other words, I just want to avoid collinear situation. Is that clear? If I have a wave packet going exactly together, same momentum, I will be able to find a certain momentum when these are actually non-zero, right? I'm just basically avoiding the situation. Is that clear? So that's what I mean by we want to focus on ourselves on the non-overlapping two wave packets, which is what we do in the collider physics. So if there's one guy going that way, the other guy going that way, then certainly there's a wave packet going only that direction. There's some spread in the momentum, but at least if I just look at the center part of that, this is satisfying. Also, some collision happens, some particle coming up. Most likely that is true. And in reality, when you produce something, when you collide something, there can be some radiation which is collinear to, for instance, electron line. Okay? And there is a formalism, there is a development, how to deal with that situation. Also, in principle, the sort of derivation that we will see applies to the collinear situation also, but I will make a comment on that. But for now, let's simplify our situation, just assume this is the case. Okay? So there's a non-overlapping wave packet, and then we will talk about LSD reduction. Any question?
저기 K1과 K2의 원주 인덱스가 아니라 F에 나오는
Yeah, I was thinking that when I was looking at this. Very good. Okay? So profile. Yes.
안에 그리시는 거 보고 아까 생각한 K1 F1에다가 원 쓰고 K에다가도 원 다 쓰는
Oh yeah, so this I'm half correct. This I was morally correct. Technically it was imprecise. Now it's okay. Any other question? Is that situation clear?
When you're claiming the equality in an state,
You say quality?
equality,
Equality. Okay.
are the in an states corresponds to the previously defined in an state.
So you're asking whether this definition is consistent with asymptotic state, the definition that we did.
Yeah.
Okay. So I believe so. I better be. So let me remind you, because we will also have to do that. So let me remind you the definition of asymptotic state. Okay. So suppose this is a state which evolved under a full Hamiltonian, like so. And then suppose this is my free state, which evolves under, for instance, like that. Okay. And the definition of in-state was that, so now let me label in. So this is the condition imposed on this. Definition of that goes to 0, right? Which literally mathematically means it looks like the first state in the far past. Now, let's just talk about a minus infinity case to be concrete. And so, first of all, are you happy to take this is the same notion of that in this equation? Just to see which part you might have a question about. So this, we have shown it, right? This is what we showed last time. Given the projected operator, if we're acting on the vacuum, it basically literally projected the one particle Hilbert space vector. And not only that, it literally produces a state with profile F1 in, like, for instance, minus infinity time. Right? On the other hand, this, without a projection, not necessarily a free particle field operator, right? This is a horrendous operator in general. But in this limit, it gets projected onto, like, literally one particle free propagating mode. So that's, in a sense, exactly the definition of instinct.
Exactly.
So, I mean, at finite time, does this look like a free particle state, first of all? One particle state?
Yeah.
No. The projection happens by this infinity. Recall that without an infinity, multi-particle state will not be projected out. And this is capable of turning on all possible, it has overlap with all entire Hilbert space vector. Projection happens at this infinity time, and this operator is genuinely projected onto the single particle propagating state with profile F.
Then you have better to denote the expression without limit t time goes to minus infinity to the in and out state.
This one.
Yeah, so without that expression, the phi RF.
Yeah.
That
Without
corresponds to in and out state, isn't it?
Oh, you mean without taking this, you can, yeah, okay, I understand your point. Yes, so you might want to say that, isn't this already sort of in state?
Yeah, that is
Yeah,
state.
yeah.
Then if you take limit, that
Sure. It satisfies that property. That's what I was trying to say, right? This state does satisfy this projection property, or limiting property.
what is the state corresponds to psi 0?
This is literally free particle state. So if you want to talk about the one particle, this is literally one particle momentum state, eigenstate. Or whatever, the wave packet state, like a clean wave packet state. This is a free Hamiltonian state.
confused me fundamentally because in the construction of that in and out state we didn't have used the Hamiltonian at all.
Well, sure, but okay, probably is your confusion that I put in and out here, which is the result of taking infinity?
That is the one confusion.
Okay, well
point.
that is sort of, if you like, a little bit sloppy notation.
And apart from that, I'm also curious because in the previous lecture we do not mention any Hamiltonian as
Well, no, we did. So in a sense, this is a renormalized operator associated with the Heisenberg picture operator, and I know this exactly transforms like this. Okay, so that operator was born out to be Heisenberg operator that transforms under full Hamiltonian, and this is just a renormalized version. Okay, and that's one. And we took a general operator, which has a non-trivial overlap with the one particle sector. That was the only condition we imposed so far. And then we showed there's a specific construction that projected that to a one particle sector in the limiting process.
yeah.
So that's the up to, like whether you put the in here or there, that's exactly the definition of a synthetic state, right? General operator can do many things, but you can project it to the one free propagating sort of particle state. That is a synthetic state. Okay.
So anyway, the notation then, so going to the notation.
Yeah, you want me to put this guy as my instant? No, I still want to use this. Why?
That is not.
I understand. I mean, I see you're purist, but you may want to put in as this object. I understand what you're saying, but this is just an indication that as a projection, it's labeled by this. This is a conventional notation. Okay, modular that understanding.
That state is just two pre-right state, right?
No, this state looks like the free two particle state.
Yeah.
That's all. This is basically telling me what is the snapshot of this state at time goes to either plus or minus infinity. Any other question? Okay, let's move on. At least we want to hit the punchline. So now we know how to deal with asymptotic in and out state. So then I'm gonna give you the statement made by those gentlemen, and then we will prove. Okay, so what is the statement? The statement is the following. The claim is, well, let me use in terms of the G1, G2, S minus 1, F1, F2. In fact, I think this should be 0. We'll see. Okay, is equal to a big expression. So let me see how they design that. Equal to okay, let me write this way. So pi of out. Okay, but I'm gonna only keep O, 1 and 2, and then out stars, which means that I have a G1 star, G2 star. Okay, and then there's also in, but I'm gonna basically put only I, 3 and 4. Times this is the statement we want to prove. So what we wanted to see is a given Green's function in terms of renormalized operator. Again, you can do it everything in terms of a Heisenberg too. How do we extract the S matrix that has a in state specified by the two-way packet our state specified by the two wave pancakes. Okay? And then the task is that this is what you need to do. First, we will prove this, and then I will give you how to think about this equation, both in sequential space and also momentum space. Okay? So there will be more diagrammatic picture can be attached to this equation. Okay, that's the goal. Let's see. Remember, if you already recall, so we have a projection operator for 2 in state specified by the F1, F2 with the Klein-Gordon equation according to that. Okay, so in principle, even allowing different mass, right, for those two. And then you have also projection operator imposed by the out state specified by the, again, 2 profiles. Okay, wave packings, G1 star, G2 star. And then basically you project it onto, therefore you will turn this guy individually into basically the projected operator, as you will see. And then you will see that gets to finally this equation. So let me call the top equation to be left-hand side. Is that a ridiculous thing? So I'm reading this as left-hand side is equal to right-hand side. So I will basically take the right-hand side and just start, manipulating it, and eventually show that it is equal to the left-hand side. Okay, so that's the game plan. Is that clear?
No. F1까지 있는데 지금 F가 왜 4까지
Oh, that's okay. That's mislabeling. But I wanted to. Okay, let me change. Reform. I just wanted the 1, 2, 3, 4 labeling, but I was hoping everything works out. Now is that clear?
G에는 왜 index가?
There is G O runs 1, 2, so G1 star, G2 star. I stressed I'm gonna only put I stressed I'm gonna only put I. Okay? Is it still advanced notation scheme?
Yeah.
Okay, good. Ready? So let's jump in. So as a first step, let's just apply the one of the first projection operator. So can I call it this looking thing as a projection operator with the profile F and then in, and then can I call this as a projection operator with the profile G and out? Okay, so let me just do that, because I don't want to write everything again. So let's first perform projection operator with the F, whatever, 2 or 1, 2, and then in. So let's just do that. So right hand side, we still have 3 other projection operators. Okay, so projection of out of G1. Projection out of G2, I still have that, and then projection operator in of F1, I still have that. Now, naively, if you perform that, if you recall what this thing does on an operator, so now I'm doing which one? I'm ready. Let me do 4. Sorry, okay? Oh, was that why there was some weird sound behind me? Okay. Something. Okay, good. Okay, then what do I get? I get the following. T4 goes to minus infinity. T4 goes to plus infinity. And then time ordering. Renormalized x1. I have to write all this. And then I will have F4 T4. Yes? So I just did an honest projection. There can be one subtlety. Eventually this is true, but there's a one subtlety. Let me just mention it, and then we just pass on. So there's a potential subtlety. So that subtlety is the following. When you prove, when you show that acting this projection operator on some operator, in this case phi r, to turn that into this projected operator, what you have to do is that given some operator A here, okay, so you can split this into time derivative and the spatial derivative. And there is a time derivative, right, acting on A. In this case, A will be this Green's function. Because of the time ordering, okay, because of the time ordering, this will have a bunch of a theta function, like Ti minus Tj, another theta function, and so on, okay? So when you add the time derivative on this thing, obviously, the first heating will turning into theta function will give you a delta function. So what I have written here is true if I forget about this subtlety, okay? Meaning, if I assume that the entire time derivative, this is Green's function, has the theta function part and only acting on these operators, that's what I will get. So now, why can I just forget about this? Well, in this case, this term makes a contribution only if there's a coincidential point of the two times, okay? But then, when I set up the Green's function, I will assume that there's a well-defined ordering of the T1, T2, T3, T4. So I'm just gonna work under the assumption that there's a clean separation of the 4 different times. Okay, 2 different times from this past, and then another 2 times in the future. Okay, so I will gloss over physically, which makes sense because I don't have to work engineer the situation where somehow there's the exact coincidence of 2 times. So if I just take that assumption, if you like, then I don't have to worry about what happened because of this. Okay, and so I will just apply the 4 times of a projection operator, assuming there's no coincidental time point. Okay. So then, if I go on, so that's the thing. So now let's actually talk about one by one. Well, so the first term, when time goes to minus infinity, because of time ordering, that means that I have to move this guy all the way to the vacuum part, right? To the right of everybody, correct? So this term basically will give me, this, and then all 1, 2, 3 guy. And then outside of the time ordering, I will have 4, T4, acting on the vacuum. And this, we know that will just give me T4. That's what we talked about. It acts like a creation operator.
오늘 등록한 서킷에 대해서 그 T1부터 T3까지는 되게 무한한 시간에
I'm just assuming there's a 3 fixed time.
근데 이제 T4는 갖다가 무한대로 버리기 때문에 절대 저 델타 펑션에 컨트리뷰트 할 수 없다 이렇게.
You can say that. But I just said that the way I said that because eventually we will take the limit for everybody.
각각 지금 이렇게 하나씩 칠하면서 이렇게.
Yes, but in general you might say in the process, if I send them together, meaning whether that notion I should care about ordering of the taking a limit. I'm saying so long as we just work, say to be safe, under the assumption that I never worry about coincidental point, even if I change the order of the limit, or even if I send all 4 3 times to send infinite simultaneously, I can still assume that there's no coincidental point and don't worry about this delta function contribution. But in this particular discussion we are doing, you can take what you said, meaning let's take a 3 fixed time for 1, 2, 3. And then we're going to send the 4th time to infinity. So yes, therefore no overlapping. But I just said that what I said, again, to be generally just safe about this subtlety. Okay, so that will give me one of the state, wave vector state. What about that? In that case, this one, well now I have to move this guy to the left of everybody. F2, T4, 4. And then there's a rest. Let me just call that rest. This is my notation for the rest, meaning all this. And we know that this should be 0, because this doesn't act like annihilation operator. It only has a creation operator. So the first exercise, first limit, only give me the 1 contribution. Okay? So that's that. So let's actually write it down. So then keep going, right hand side. is projection of out G1 profile, projection of out G2 profile, projection of in F3 profile, and then what do I have is now okay, so that's all I have. Okay, good. Now let's take the second thing. So let's add that guy in F3. So then you will turn this guy into, again, that operator, right? So now, hopefully I don't need to write everything, but I will write enough. Now this will turn into outside of the X. F3, T3. Again, I will have a one limit where T3 goes to minus infinity, and then it goes to the plus infinity. You see that the second limit, again, you have to put this operator to the left of everybody by time ordering, and you hit the vacuum explicitly, you get 0. Is that clear? So you will not get contribution from here again. And then when you hit this guy when you move this guy to the right of everybody, because you're taking minus infinity limit, basically you have to add this guy onto this one particle state. We talked about that, right? So there was one particle way back in somewhere, then I'm hitting the second time, so long as there's no cordial connection between the two, I should just prepare a two particle state. So the answer to this part should be out G1, out G2, and then I can even squeeze in to right here. F3, F4, but I know what exactly that is, according to my notation, or Coleman's notation scheme, that's actually in-state, because both comes from t goes to minus infinity part. Okay? So they are labeled as this, t goes to minus infinity. Good. So two more things to do. Let's continue. And then we will get a bit of subtlety. Is it a good idea to keep this or not? Yes, I think so. I think so. Okay, so let's now move on to the third step. So we're gonna now do this. Okay, so that's done. We are doing this. So what do we get? So therefore, right hand side is I still have a 1 G1, and then times. Now there is a flip over. The T2 goes to first plus infinity. T2 goes to minus infinity. And then let's actually write it out explicitly. So there's a time ordering of F2, T2. Okay, so that's what we have to do, right? So now we need to deal with this projected operator. Oh, no. This is, sorry about that, G2 dagger, right? Remember? Because that was coming from this, G2 star projection. And recall that this behaves like annihilation operator, right? Annihilation operator with a G2 profile. So this one, by time ordering, you have to move this guy to the left of everybody. When you hit a vacuum, you create the G2 state. Okay, so let's write. There's a projection of G1 times. When you do it, you actually generate G2 state. And then I don't have to put time ordering anymore because there's only one guy to deal with. F1, F2, in. That's first term. What about the second term? So by again time ordering, what you have to do is, and then you have this one, R, G2. I keep making the same one. G2 acting on F1, F2, in this. that's the structure that we are dealing with. Yes? Okay, yes, I did it correctly. Okay. What is it? What is it? Well, it's not so clear, right? It's not so clear. The only clean statement you can make about, now, let me give you a recall. The only clean statement you can make about this operator is you have a certain state, right? If you had, so more precisely, the only clean state you can make is, for instance, if you had this operator, G dagger, acting on a certain state, you know this is 0, because it's an annihilation operator. That's clean statement. Another clean situation is when you take this guy, G dagger, some state, vacuum, you know it creates the G state. So these are clean state, clean picture that you know what to do. Now, this is not so clear now, right? There was a 2 in state prepared, but in the minus infinity, you're performing this. Because this, you don't acting this on either one particle state or the vacuum state. It's not so clear what it is, okay? So for now, I'm just gonna give a name, because I don't know what that is yet. I'm just gonna call this the beta state for now. But eventually our final result will turn out to be the case that you don't actually need to specify exactly what eta is. Okay? Okay, so that's how much we can say at this step. So let's keep moving. Let's finish up the last one. So I have this, I have this. Okay, so now we need to do this. That's our last thing to do. So I think it's better if I actually write here. So let me just do it here. If I do it, how do I turn it off? So I will have T1 goes to plus infinity. T1 goes to minus infinity, acting this guy. Okay? So I have to now turn this guy, well, maybe right. F1, T1, F1, F2, oh no, again F. Okay, and then G1 dagger, and then I have that. So that's what we do. Okay, so I just turn this into projected operator, and that into projected operator. That's what I did. Okay, now it's about we are about to see the punchline. So at least probably you want to wake up now. Okay. So we just did an honest job of projection. So let's ask. Now we have to deal with the 4 terms. Let me do it one by one. Let's first do this. So the first, this, what is that? Now I'm gonna take this annihilation operator acting to the left, where I already had a 1 particle state, right? Just like we discussed about producing this symptotic in state. This is literally a conjugation version of that. Nothing different, right? You had a 1 state, and then you act on the second guy. So long as I get causally disconnected, it should just give you a G1, G2 state. But now they are labeled at time to infinity, so that's what we call out state. And then we will have F1, F2 in state. Okay, all right. At least we see one case that we really wanted to see. Okay. What's the next one I have to do? So let's do this. Okay, so that's also easy because I know what this guy does if you acting on the left vacuum. So that's, let me even keep track of the sign, minus G1 8, right? That's what we get. What about this? What do we get? So now we are taking time minus infinity and acting on here. What is that? Eta prime. Oh, I like eta prime for a completely different reason. Okay. What is this? What is that? What is that? So let's ask it here separately. Let's write. So we're asking time 1 goes to minus infinity, and then G2. Because I'm writing because it may be not completely clear at the beginning, and then F1, F2, right? So that's what we're asking. So again, recall what this guy does to you. Okay? This, you can say you have some arbitrary state, psi. Given a psi, you're not acting on the vacuum, but you're acting on some particle which may be far away. It wouldn't matter how you act this guy, right? The only difference is that you had a one particle state, so the only difference of this case compared to this case, remember this is literally the same. The only difference is whether I'm using that as a time plus infinity or time minus infinity. That's the only difference. Is that clear? And what difference can you get? Do you get because you're flipping this to the from a plus infinity to the minus infinity, where you're still producing that guy, but now you label the state according to how it looks at t goes to minus infinity, right? That's the only difference between that and that. Is that clear? So this should be G1, G2, but now everything is labeled at time minus infinity, so that's in state. Okay? So let me write. So this gives me, because of the minus sign, minus G1, G2, F1, F2, here in, here in. And then the last one. Okay, so what is that? This minus sign, then minus sign cancel, so plus. And then now I'm acting on that guy on the left. Again, for one particle state, it doesn't matter, right? It's minus plus. So I'm still producing one state overlapping with that. Is that clear? Okay? So, good. So this guy actually cancels that, and we're only left with this minus that. Let's just work it out what it is. So we need to basically resolve or understand this expression. So after all this exercise, we are left with the following. G1, G2 out, in, minus, okay, at the risk of doing repetition, let me write this. So this is what we have now. Okay? Is this what you expect to see? Well, one is in and out, the other is in and in. This, if you recall, again, definition of in-state and how we defined a S matrix. The first one is literally, because let me recall here. Let me remind you, all right? So the in-state is defined in is equal to, sorry, I forgot the time evolution, so I have to write it in. In is free particle state. Okay? Now I can rewrite this as follows. In can be t goes to minus infinity. I just move this guy. IH not t is free guy. And then if you recall, this was literally interaction picture time evolution 0 to t, but there's a conjugation. It is actually conjugation. So this is actually 0 t. So in-state can be written starting from the free particle state in terms of this evolution. You can do the exactly same thing So you can do the same thing for the out state, and then ultimately what we found, so this is connecting from here to here. So that was literally the definition of G1, G2, but free state, and then you will get a two of this guy overlapping. One goes to minus infinity, the other goes to plus infinity. That was exactly the definition of S operator, and then S, F1, F2, again, 0. So that's the first piece. If you do the same exercise for in and in, you get a UI 0 to, 0 t where this goes to minus infinity. You get the conjugation of that. So you have a u dagger u, which is 1. Okay? So that will be G1, G2, F1, F2, 0. Or you could just say that you have this with S minus 1. Okay, so that's the S matrix. What have we done? Well, we took a pretty general endpoint correlation function, a Green's function, made out of some renormalized operator, which has non-trivial overlap with the one particle sector. We performed the projections either in terms of positive frequency or negative frequency. Positive frequency projection turning into things, corresponding operator into a in state, the other one turning into a out state. And then you get a S matrix of this one. Okay? Now, what I want to explain the rest of the stuff. You might say, entire thing is wrong because this is a 3 and 4 and 3 and 4. The entire thing is completely wrong. Okay. You should be careful in finding an example. I don't. 3 and 4, 3 and 4, you know what I mean, right? Okay. Yes. No, go ahead.
I asked my question about the ability that we define state 8.
Here.
Yeah.
Yes.
The state F1 and F2 in state F1 and F2 is defined by we perform some creation operator, two creation operator into some vacuum state.
Yes.
And if you assume that that two operators and that operator is commute because of the separation of that operators in the sense that they are causally disconnected. Then I think we can use some.
And you might say this is trivially 0.
Yes.
Yes. Under that assumption, I agree.
And that consequence may lead to the result that the right hand side is not a left hand side, but we don't have -1.
So I think if we do what you suggest, meaning if in a quantum field theory, so here, let me clarify, here I'm being general. Maybe I can deal with some field theory where this is not actually commuting with whatever operator that I use already, right? Also, not only is question about the commuting operation, because we're dealing with the time ordering, and then it's just a matter of the order of a limit I took, right? So in a way that in the order that I took already, the operator associated with F1, F2, or F3 and 4 are used up, right? And they are turning into state. I don't need to deal with this sort of operator yet. I have done the limit already. In that case, I still have this picture, okay? And to be just more general, maybe I'm dealing with a quantum field theory that this doesn't actually come in with the other two, then I have to just stick as it is, and I cannot make additional simplifying assumption. In that case, I just define this state, I just call that state to be something, maybe 0, maybe not, depending on actual theory you're dealing with. And then the point of this construction, this derivation is that the final answer is independent of that details, right, eta details, whether it is actually 0 or not. But I agree that if you're actually dealing with a specific, certain kind of QQLT, this may actually come here and you hit the vacuum first and then maybe 0. So it is actually a good exercise that you may actually exchange the order of a limit. So you can take this limit first, and then you will not get any contribution from this side because you hit the vacuum already. In fact, we have already seen that. When we took a first P4 limit, that's the order we did. there was a two-part. One hitting the t to minus infinity, which we got f1 state. But then when we hit that guy to the plus infinity, we just get 0. Because that limit, we get clear 0 from that. But if we exchange the limit, maybe the t plus infinity limit of t4, we will get something like this object. The point is that this shouldn't depend on the order of the limit.
The reason I said that because in the Pascal graphic book,
Yeah.
there is a derivation of LNC reduction formula, but that formula doesn't have -1 in that book. So
You mean this?
yes, this book doesn't have -1.
Okay.
So I was confused about.
Oh, is the starting point the same or?
No, derivation is absolutely different.
Yeah, I
from
sort of not remember, but I studied that derivation. I don't recall all the details. But here, at least, I will mention to the momentum space picture. Okay, and then you will see this basically same sort of picture that you see from the past game. Maybe there is this -1 difference. I don't know. Or we'll see. But I see. But I think even if you assume this is commute, do you think if you assume this always commute, which is not the case probably in any QFT, all the QFT, right? This operator may be anyway. But then, do you think that they can actually sort of not resolve? Can get rid of the -1 sign? I don't know. Probably not. Yeah, because still I have two terms, right? Still I have this, then that. That seems to always cancel regardless what this state actually is. Yes.
About the G1, G2 in state
Yes.
over there.
Yeah.
From the derivation, the first G2, we took the limit of T2 to plus infinity, and for the G1, we took the T1 to minus infinity.
Okay.
But we're defining that kind of state in a space-like separation. But if we took the t's to plus and minus infinity, how could that be space-like?
So
like separation.
Okay, maybe this question is two parts. First question, maybe where is that? Yeah, this is right. We're talking about this piece.
Yeah.
And it may be true that we have to go back and check. G2 state is from when T2 goes to plus infinity.
Yeah.
But like I said, for one particle state, before we actually creating a two particle state, one particle state is basically can be both in and out state. Because it's a free propagating from into the out, right? So that state, as a one particle state with the profile wave packet G2, look the same in and out. Only when we act with the second guy to create a two particle or multi-particle state, then you will have a specific meaning, right? So that's the sense I think we can decide that it is actually instant in that sense. You know what I mean?
Okay.
Even if G2 was constructed from the t goes to plus infinity, but again, it is the same as constructing that guy minus infinity because as a one particle state, it was what it is. Did that fully answer your question, or there's still the second part of the question, or if there was any?
No, I'm
Okay. Okay, let's move on because I want to spend at least 6 minutes to give you momentum space picture, which is important. Okay, so now, good. Let's take now. Hopefully, we established this thing, and now this mathematical expression holds even if you take F's and G's to plane wave profile. Okay, so far we've been assuming wave packet because only then we can actually talk about the localized particle and the collision and so on. But just mathematically, you can take this limit to the plane wave, and this formula still works. And then you can take it as a definition of S matrix for plane waves, even though then you have a lot of physics questions. What does that mean, right? So let me therefore discuss momentum space picture. So far, because it's very just formal derivation level. What is it? So let's talk about this in the momentum space. So going to the momentum space, And we want to now discuss everything in terms of original Heisenberg picture operator. Okay? So first of all, I could have defined this object, endpoint correlation function. I could have written as a renormalized endpoint function, x1, xn. Okay? So that's this object. Now, recalling the fact that the relation between Heisenberg and the renormalized object is z to the minus f. Okay? Then I can rewrite, if I had a renormalized endpoint function, I can rewrite this as basically replacing that. So I will have a product of r, zr to the minus f, and then unrenormalized but Heisenberg picture Green's function. Okay, I just plugged in phi of r. Remember, that's just constant. It doesn't depend on the momentum. Okay, so I can just rewrite it as that. Okay, so that's the first job I can do. Now, so I can write this, and then eventually you can do the Fourier transform because I want to go to the momentum space. So that will get you wave function renormalization factor, and then momentum space. Okay. So I'm doing this because I don't want to do like line by line Fourier transform. You can do it, but since the quick translation is possible. And what about this factor? So what about this factor? So this projection factor. Now let's take let me take a plane wave limit just to simplify the notations. Okay? So I'm just gonna take a plane wave limit. So then this projection factor in the momentum space turning into I times basically p squared minus p squared plus m squared. Okay, so if you just pass on to the Fourier space, momentum space, that's what you get for each of those projections. And then you should convince yourself that this is nothing but inverse. Okay. Finally, I mean obviously S matrix part will be something like initial momenta, final momenta, S, and then initial. Okay, in the momentum space. So then we can assemble everything together to get the following expression. So therefore, we get the following. Let me remind you one of the things. So 2-point function in Heisenberg picture, in general, if you take a on-shell limit, meaning if you have a pole of 2-point function, you get wave function factor p squared minus physical mass. Okay, so that's how it looks like. So if you try to assemble everything together, what do you get? So you have a zr to the minus half factor. On the other hand, you just have an I. So in order to express everything, so you will get the following expression. So basically, that's the left-hand side, okay? There's an S matrix in the momentum space. And then we need to sort it out. So we're actually taking the other limit. Okay, the other limit. Do I have time to change my mind? I do. So let me change my mind a bit. I mean, so far everything good, okay? But this times, so now I'm gonna move everything to the other side, okay? So then you will have a product of out, and then propagators, O, PO squared minus MO squared, and then everybody in, and then you have the Green's function, all momenta, K and P. I have to put in back something correctly, so that is, there's extra factors. You can convince yourself, for all external x, we have to multiply zr, okay? Because you only had a zr to the minus half when actual complete 2-point function in Heisenberg picture has a full z to the first power, Okay? Because of that, you have to just compensate that. Now, what's the physical picture of this? Take a Green's function. Okay? This is endpoint Green's function. You have some number of external legs in out, some number of external legs in state. Now, you're going to multiply square root of a renormalization, this wave function renormalization factor for entire external legs. Then, this thing is full two-point function, meaning propagator, which I'm drawing as a block. Okay, so this is not just a free propagator, complete general propagator. You zoom into on shell. So now you actually zoom into everybody. Go to the on shell. The answer is the fact that you are stripping out full propagator means that out of your thing, you just amputate those external legs. Up to this factor, which you have to multiply, the residue of that thing is asymmetrics. So I think everybody should be minus inverse. Sorry about that. Because inverse was sitting on this side. Oh, sorry. Where is the equality? Where is the equality? Equality is this. Okay, sorry for the confusion. So let me stress that again. I will say two sentences. That will be. So the crux of an LHC reduction formula in more analytic structure way is that given an endpoint Green's function in Heidelberg picture, you go to a n-pole part in your momentum space. Every single argument, you go to the simple pole region. Okay? You go to the simple pole region by going to the on shell. Up to this factor, you have to multiply the residue of that n-pole part of the momentum space complex plane is the S matrix. In the sense, this is the most singular part of the momentum space of endpoint Green's function. The residue up to this factor is the S matrix. Second way of saying it diagrammatically, take the endpoint Green's function, multiply that for every external x, amputate full propagator, and then the rest is the S matrix. That's the LHC reduction formula in momentum space. Okay? Good. So that's all for it. If you have a question, I'm happy to take outside the classroom. So that will be this will be the last lecture from me, and I would like to thank all of you for many interesting questions and illuminating interactions. And I hope you learned something. And if you didn't, good luck. Green church is coming. Anyway, so thank you. I'd like to thank everybody for your participation. Thanks.